Hello YouTube and welcome to this presentation where we'll talk about the computing speed of different data transformation engines. Data transformation engines are also sometimes referred as ETL, and ETL is the acronym of Extract, Transform and Load. This presentation is composed of two videos and you are actually watching the first video, so let's start. But first, why would you care about the speed of your ETL? Well, that's because each time that you use data to do anything with it, to create predictive models, to create reports, to create KPIs, to improve processes, etc., you always end up working inside an ETL. Forbes says that a traditional data scientist spends more than 80% of its time doing data transformation with an ETL. This fact is also sometimes called the 80-20 data science dilemma, and you should Google that. By the way, this is somewhat ironical that the data scientist job has been described as the most sexiest job of the 21st century. You see, many people find the data scientist job sexy because they think that it involves working with very complex algorithms that learn by themselves. And it's true that it's somewhat cool, but in reality, when you actually look at what these professional data scientists are really doing, you see something totally different. A good data scientist is just doing good old ETL work nearly all the time. Unfortunately, ETL work is sometimes perceived as an uninteresting and boring work. At least compared to machine learning and AI, ETL is definitively not a hype word. And I couldn't disagree more. It should be hype. As a data scientist, you want to spend your time creating the right KPI and the right features for your model. And this requires so much creativity and ingenuity. This is just fun work to do. And this is actually pure ETL work. So the Forbes magazine is telling you that ETL work is important. And I couldn't agree more. The InfoWorld magazine is also telling you that ETL work is important. And finally, the New York Times magazine is also telling you that ETL work is important. It's actually even more important when you are using an automated machine learning tool such as TiMi-Modeler. That's because with TiMi-Modeler, the actual time spent in the modeling process to create your predictive model is usually reduced to only 5% maximum of the whole project. This means that with TiMi-Modeler, the ETL work now covers at least 95% of your working time. In this condition, you'd better find a good ETL. So, to summarize, now more than ever, a fast and user-friendly ETL solution for high-velocity data transformation is the most important element for the comfort, the efficiency and the productivity of any data scientist. So, now that we have established the crucial importance of your ETL tool, let's have a look at two important ETL tools, Anatella and Spark. More precisely, let's look at the speed and the efficiency of these two tools when it comes to pure ETL tasks. Let the showdown begin! So here are the two contenders. On the left side, you have Spark. Spark is one of the most well-known ETL tools on the market. Spark is recognized to be several orders of magnitude faster than any other tool inside the Hadoop ecosystem. For example, Spark is 100 times faster than MapReduce or Hive. And this is why so many software vendors are using Spark behind the scene to do all their data transformation. For example, Databricks, Dataiku and IBM Analytics are all using Spark as the underlying computing engine to do nearly all their data transformation. Spark is a distributed in-memory tool that will typically use all the combined RAM memory of all the servers inside the PC cluster to perform the requested data transformation. The most efficient way to run Spark is to write Scala code. This is typically done in a shell or a console like this one. And on the right side, you have the other contender, Anatella. Anatella integrates with the most common languages found in data science, Python, R, and also JavaScript. The most efficient way to run Anatella is to design a data transformation graph like this one. For example, this graph reads a data file, filters out some row, aggregates the data, and finally displays a bar chart inside a user-friendly graphical interface. A trained business user can design nearly any data transformation by himself using only his mouse. Basically, the complexity of using Anatella is very similar to Excel. Actually, you should know that the language Scala that is used inside Spark is very different from all the other coding languages presented in this slide. It's a functional language in opposition to all the normal declarative languages that are used everywhere else in the IT industry. For that reason, Scala is really difficult to master. It's a well-known fact that it takes years of training before a coder gets any kind of productivity in Scala. So we won't compare the time required to create a new data transformation in each of these two tools, because in this case the clear winner is Anatella, since it offers a much easier to use interface and you don't need to write Scala code. So in the next slide, we will only benchmark the runtime speed of these two ETL tools. More precisely, we are only interested in the time required to run some specific data transformation. Let's now talk in more details about the benchmark in itself. Surprisingly, there exist very few benchmarks available to test the runtime efficiency of different data transformation engines. One of the universally recognized benchmarks is the TPCH benchmark. This benchmark is recognized as a very relevant and very serious benchmark by nearly all the most common software vendors. For example, very famous names such as Oracle, Microsoft, Teradata, IBM, they all have participated to the TPCH benchmark. The objective of the TPCH benchmark is to run 22 SQL queries as fast as possible on a reference database that is composed of a dozen tables. You can see the table there. If you want to skip the explanation on the TPCH benchmark, you can just click here. The TPCH workload is interesting because this workload is universally recognized as interesting and representative of the data transformations that are commonly used in the everyday life of all data scientists. So for a data scientist, it's really interesting to look at the results of the benchmark. And the rules of the benchmark are quite simple. The winner is just the fastest tool, so the speed. You just need to run these 22 SQL queries as fast as possible, and the tool that takes less time wins. Actually, if you look at the documentation of the TPCH benchmark, you will see that the rules are not as simple as that. That's because some database vendors try to cheat. For example, they pre-computed in advance all the joins between all the tables. This way of cheating is called materialization. You pre-compute in advance everything, and then when you actually run the benchmark, you don't compute anything anymore, you just read the pre-computed results out of the hard drive. This is really cheating, and materialization is forbidden when participating in the TPCH benchmark. So for the TPCH benchmark, you must run the 22 SQL queries on a database, and you can generate this database at different sizes, from 1 GB to 1 TB. We'll see later a table with all the different timing results on these different database sizes. For the largest database size that we tested, the 1 TB size, the table named line item contains 6 billion rows. Each row represents the purchase of one product from one customer. This is 6 billion rows. I must stress out that we are working on a scale that involves tables with billions of rows, not millions of rows. It makes a difference because when you manipulate data tables with billions of rows, most software are crashing. Not Anatella, of course, because Anatella handles a much larger data volume, but it's worth noticing. Now, to be as fair as possible in the benchmark, we did run all the computation with Spark and with Timmy on exactly the same machine. This is a standard €2,000 computer from LDLC. It has a Core i7 CPU with 16 gigs of RAM. The standard configuration from LDLC had only a very small SSD, so we added a standard €400 SSD from Samsung. All in all, it's a pretty cheap server that we have here, around €2,500. Again, to be as fair as possible with Spark, we selected the best operating conditions to really give him a chance to shine, or spark. For example, we use the latest version of Spark from January 2019. We stored all the data in the Parquet file so that the data access speed is the best that you can get in Spark. We did not store, however, this Parquet file in HDFS because the HDFS layer in the middle between Spark and the SSD drive was slowing down everything. We allowed Spark to directly read the Parquet file from the SSD drive without any slow intermediary step. And finally, we did run all computation in a non-interactive session, as if the queries were running during the night. This makes a big difference for Anatella, since Anatella possesses an interactive mode that allows near instantaneous computation of the most complex queries, thanks to a unique advanced data cache system. Originally, the TPCH benchmark was designed to run only on databases. This is why, if you go to the TPCH website, you will see that they only accept timing results for databases. But in our case, we don't have a database. We have two more exotic systems. We have Spark and Anatella. So we converted the 22 SQL queries from the TPCH benchmark to Scala to run them directly inside Spark, and to some data transformation graph to run them in Anatella. The TPCH benchmark is so well known that it has already been implemented in nearly all data management platforms, and we quickly found on GitHub the optimized Scala code for the whole TPCH benchmark that was coded by a professor from the Purdue University in the United States. Finally, it's important to remind you that it's not enough to run the benchmark quickly. You must also obtain the correct response at the end. For example, for the query 4 here, the official result, you need to validate that you get the same result as these tables, otherwise it doesn't count. So we validated everything and everything was okay. So these are the raw timing results for the benchmark. Presented like this, it's difficult to get any conclusion out of it. So we won't lose our time looking at this table. We'll analyze this table step by step during the next slide. But before we dig deeper into the timing results, I'd like to make a little digression to talk to you about the Amdahl's law and the incompressible times. If you want to skip over the technical details related to the Amdahl's law, you can click here. So what do we see here? We see some timing results from the first query, query 1 of the TPCH benchmark running on Spark. When Spark uses one CPU or one executor in Spark vocabulary, the query 1 takes 184 seconds to execute. When Spark uses two CPUs, the running time drops to 99 seconds. The running time dropped to 80 seconds on 3 CPU, and on 5 CPU it's 63 seconds, and when you have 100 or 1000 CPUs, the runtime stays at 37 seconds. These 37 seconds represent about 20% of the initial running time of 184 seconds. In this case, we'll say that for the query 1, the incompressible time is 20%. It's not possible to reduce the running time below 20% when adding a very large number of CPUs. Let's now formulate the Amdahl's law. The Amdahl's law is this equation here. It just states that there exists an incompressible time below which it's impossible to go, exactly what we just saw on the previous slide. In the previous slide, we saw that the incompressible time was about 20%. In this slide, the incompressible time is illustrated in blue here. It's also about 20%. The incompressible time is named S in this slide. In opposition, the compressible time, represented in green, is 80%. It's the rest of the time. But as soon as you use 2 CPU instead of 1, the compressible time in green drops to 40%. It's 80 divided by 2, simply. On 3 CPU, the compressible time drops to 26%. On 4 CPU, it's only 20%. So to summarize, the Amdahl's law says that the following: the total running time of a distributed computation system is the sum of the incompressible time, S, plus the compressible time, 1 minus S, divided by the number of CPUs. S plus 1 minus S divided by N. So what's happening when we increase the number of CPUs to a very high value? Then the green bars here will be reduced to almost zero. This means that in the best case, when running on an infinite infrastructure, the total running time will still be equal to the incompressible time, which is here in blue, 20%. In other words, on an infinite infrastructure, we are actually dividing by 5 the running time. We go from 100% to only 20% of running time. In technical terms, we'll say that the maximum speedup that you can obtain is 5. So this is interesting. When the incompressible time is 20%, the speedup is 5. Let's keep that in mind. So this slide is exactly the same as the previous slide, with a small difference. This time the incompressible time is 50% instead of 20. So you see that if the incompressible time is 50% and if we are running on an infinite infrastructure, the maximum speedup is 2. We'll only be able to divide by 2 the running time, going from 100% to 50%, dividing by 2 the running time. So it means that even with a cluster that contains thousands of nodes, you only get a speedup of 2. Then not at all what I would expect from a correctly designed distributed computation engine. I think that we can all agree that when the incompressible time is 50%, like here, it just means that the distributed system is not working at all. This is a chart that comes from the Wikipedia page about the Amdahl's laws. It illustrates really well the speedup mechanism. So this chart is a direct application of the Amdahl's law. It illustrates the speedup here on the y-axis that in function of the number of CPU on the x-axis. Let's first look at this blue line. It represents what's happening when the incompressible time is 50%. As you can see, when the incompressible time is 50%, the maximum speedup that you can achieve is only 2. Nothing new here, this is exactly what we saw on the previous slide. Let's now look at the green line here. It illustrates what's happening when the incompressible time is 5%. First, you should realize that an incompressible time of 5% is something really exceptional in the data transformation world. Very few softwares are actually able to get an incompressible time as small as 5%, and only on very special, easy cases. For example, Teradata is able to get an incompressible time of 5%, but only on a small set of easy SQL queries. And, as expected, when the incompressible time is 5%, the maximum speedup that you can achieve is 20. Personally, what I found really horrible is that the fact that you need to use about 4,000 CPUs to get this speedup of 20. This is just nothing short from horrible. I don't know you, but I was not expecting that at all. I know that there are always some inefficiencies when running distributed computation compared to a computation that runs on one CPU, but such a large inefficiency was totally unexpected for me. I don't remember what I was initially expecting, but I guess that if somebody was telling me that he is using a cluster of computers with 4,000 CPUs, I would at least expect a speedup of let's say 1,000, but actually the reality is totally different. In the best case, when you have an incompressible time of 5%, which is really exceptional, you can only expect a speedup of 20. Not 1,000, nor 4,000, only 20. That's terrible. You understand now why so many software engineers in the 80s and the 90s were completely against distributed computation engines. That's because the Amdahl's law put such a terrible and horribly small upper boundary to the speedup that you can actually achieve when using a distributed computation engine. Basically, achieving a speedup of 20 is very difficult. And it comes at a terrible cost, using more than 4,000 CPUs. So the next question is, can we compute the incompressible time of the different queries inside the TPCH benchmark? Knowing the incompressible time of Spark is interesting because it will allow us to assess if the software is well written and properly scales up when adding more CPUs. Okay. Don't be frightened by this slide. We'll analyze it slowly. To estimate the incompressible time, we'll use a well-known technique named solving the inverse problem. It's an old, very generic and very reliable method that is used by engineers and chemists to estimate the different parameters of their equations since the beginning of the year 1900. This slide uses some mathematics that are quite difficult to understand if you are not an engineer or a chemist. But at the same time, this slide is not really important to understand the rest of the presentation. So don't worry if you don't understand all the small technical boring details of the computation presented in this slide. If you don't want to know all the technical details on how to compute the incompressible time, you can click here to skip the explanation. So we'll use the inverse problem technique to find the incompressible time for the query 13. The incompressible time S is a parameter inside this equation, the Amdahl's equation that we already saw in the previous slide. To summarize, the general principle of the inverse problem technique is very simple. You basically try different values of your parameter, here the parameter S, until your equation fits your observation. So we observed how much time Spark took to compute the query 13 on 1 CPU, 2 CPUs, 3 CPUs. We also represented the same observation graphically in this 4 chart here. This is the blue line. In these 4 charts, all the blue lines are exactly the same as they represent the reality. They represent what we really observed in reality. Thereafter, we use the well-known equation, the Amdahl's equation here, with different value of the incompressible time parameter S. And this green line here, here, and here, they represent what's happening when you use Amdahl's law to compute the expected total running time when the incompressible time is 50%, 40%, 30%, and 37.9%. For example, this red point here is directly derived from the Amdahl's law. It tells us that when the incompressible time is 50% and when the number of CPU is 4, then the total running time is about 62%. And you can see on this chart there that when we selected an incompressible time of 37.9%, the two lines here, the blue line and the green line, they superpose almost exactly. This means that when I select an incompressible time of 37%, the Amdahl's equation represented in green here fits precisely the measures that we have physically observed when running Spark represented in blue. When the two lines superpose like that, it basically means that we found the correct value of the incompressible time for the query 13. It's 37.9%. Actually, we didn't try manually one by one plenty of value of the incompressible time parameter S. This would have taken way too much time, and this would have been a quite imprecise and error-prone procedure. Instead, we used an algorithm. More precisely, we used a global optimization algorithm that automatically searches for the optimal value of S that minimize the fitting errors here represented in red. The global optimization algorithm tests for us many different values of S until we found the value where the Amdahl's equation fits precisely the data point, where the fitting error is minimized. By the way, the global optimization algorithm that we used is named STEP. It has been invented by Hugh Berzini from the ULB, a university in Brussels. For those interested, we placed everything on GitHub here. So we solved the inverse problem, as explained in the previous slide, and we obtained the incompressible time S for each different queries. For example, for the query 1 and 13, it's okay, because the incompressible time is below 50. But something terrible happens for the query 17. The incompressible time S is greater than 50. And if you remember a few slides ago, we saw that an incompressible time above 50 is just terrible. It just means that the Spark engine is not able to distribute properly the workload amongst all the available CPU. It just doesn't work. And for the query 14, the incompressible time S is even higher, 73%. In this case, this is really a complete failure of the distributed computation engine. So we just saw that Spark is failing for the query 14 and 17. What about the other queries? Because the TPCH benchmark includes 22 queries in total. How many times is the incompressible time above 50%? How many times is Spark completely and utterly failing to do its job properly? So let's have a look. And I am warning you, you are about to be really shocked. We explain why a good ETL tool is essential for any data scientist activities. We explain the TPCH benchmark that we use to compare the speed of Anatella and Spark. And finally, we explain the Amdahl's law, and more precisely, a very important notion that is the incompressible time of distributed computation engines. So each row of this table contains the results of a different query of the TPCH benchmark. There are 22 queries inside the TPCH benchmark, so we have 22 rows here. The Spark incompressible time S is given in the second column here. For more clarity, I colored the background in red for all the incompressible times that are above 50%. As you can see, this column is almost entirely red. This basically means that Spark failed to properly distribute the computation for almost all the queries from the TPCH benchmark. To remind you, an incompressible time above 50% means that the maximum speedup for Spark is 2, whatever the size of your cluster, even on a cluster with thousands of nodes. The third column here contains exactly the same information as the second column. It's just the unit that changed. More precisely, we see in the second column the incompressible time expressed as percentage, and we see in the third column here the same incompressible time but expressed in seconds this time. So it's basically the same information. It's the running time that you would get if you were using an infinite infrastructure to run your Spark queries. The green column here contains the running time of Anatella when Anatella runs only on one machine. And the last column here compares the running time from Anatella to the running time of Spark. It's just the ratio of these two columns. For example, here the number 113 means that Spark running on an infinite infrastructure is more than 100 times slower, 113 times slower actually to be exact, than Anatella running on one machine. Indeed, you can see that Anatella executes the query 2 in less than 6 seconds, while Spark executes the same query in more than 600 seconds. That's a 100 ratio in between. And if you look closely at all the numbers in this last column, you'll notice that the ratio is always above 1, always above 1. This means that whatever the size of your infrastructure, the Spark engine will always be slower than Anatella running on a single server. Oui. That's really bad for Spark and for all the tools that are using Spark as their main computation engine. They are basically drop dead in the water. Actually, if you look at this table, the speed of Anatella compared to Spark might seem very impressive, almost not credible. But you should not forget that when your incompressible time is above 50%, this means that the maximum speedup that you can achieve on an infinite infrastructure is only 2. This means that it's enough to run only 2 times faster than Spark on a single machine to always beat Spark running on an infinite infrastructure. And it's actually quite easy to gain a factor of 2 in speed compared to Spark, because Spark is created using the Java language, and the Java language is very slow. It's actually just enough to code an ETL in C instead of Java, and you almost directly run twice as fast compared to Spark. And when you run twice the speed of Spark, you can always go faster, whatever the infrastructure size. Anatella is not the only software that can beat Spark on an infinite infrastructure. Actually, almost any tool coded in C can do it. We'll see a small example from a coder named Adam Drake later about that. As a side note, this comparison with Spark is really fun because it gives you a nice idea how fast Anatella is. But it's almost too easy to win because there is an obvious problem inside Spark. It should not have an incompressible time above 50%. What would have been a lot more difficult is a comparison, for example, with Teradata. Teradata is also a distributed computation system, but it does not have the kind of terrible problems that Spark exhibits here. Usually, when you run a query inside Teradata, you can expect an incompressible time around 5 to 10%, which is really nice. And then, with such a low incompressible time, it's really becoming almost impossible to beat Teradata with a single machine. So the main question that you should ask yourself is not how is it possible that Anatella is so fast? Also, I would really appreciate it if you ask yourself the question, But rather you should ask yourself, how is it possible that Spark has this huge incompressible time above 50%? How is it possible that Spark is so slow? Look here, in this column. There is a speed factor of more than 100 times between Spark and Timmy. So I must admit that the first time that I saw the numerical results, I was kind of shocked because an incompressible time above 50% is a really high number. So my first reaction was to tell Raphael, a colleague of mine, to double check and redo all the timing results. Myself, I rechecked the script that solves the inverse problem. But I just couldn't believe my eyes. So I started to search the internet for some websites just to see if there are other people that also found that Spark has a terrible incompressible time above 50%. So if you are not interested on the other benchmarks that we found, you can click here to skip this part of the video. And I quickly found a scientific paper named AMDA Law in Big Data Analytics Alive and Kicking. This article was published more than 1 year before we made our own analysis. And this paper is written by 4 scientific researchers. 2 of these researchers are from famous and respectable universities in USA. One is from Intel and the last one is from Google. They use a benchmark named TPC-BB that is very similar to the TPC-H that I am using myself. The main difference is that the TPC-BB has a much wider scope. It has a much higher number of queries because in addition to ETL processes, it also benchmarks machine learning algorithm and big data algorithm. The table here shows some benchmark results for a few representative queries extracted from the TPC-BB. Inside this table, each row is a different query. The 2 columns here represent the size of the database used to run the queries. Once again, I'll color the background in red for all the incompressible time above 50%, and in green for those queries where the incompressible time is below 20%. You should see here that there are plenty of red cells. That's exactly the same kind of disappointing and unexpected results that we found ourselves when we ran Spark on the smaller TPC benchmark earlier. So what does that mean? It just means that we are not the only ones that noticed that Spark is failing to do its job properly, that Spark is not able to properly distribute the workload on several machines. Basically, Spark does not scale up. I feel kind of terrible for the people that spend so much time learning this technology, because very often they have invested several years of their life in learning Hadoop and Spark, because it's really not an easy learning experience. It takes years to master this technology. But the truth is, this technology has deep flaws and it does not fulfill its promises. Sometimes, some of these people believe that we were not fair with Spark during the TPC benchmark. But the fact is that we did all the work required to make sure that Spark runs as fast as possible. For example, we are sometimes suspected of running a very slow and very bad Scala code inside Spark. The thing is, we didn't write the Scala code. It's a university professor, Mr. Savas Savides, that did all the Scala code. This means that the Scala code that we use for the benchmark is just really representative of what a very experienced coder would do if it invested several years of its life to learn Scala. Actually, if you look at the Scala code that is used in the vast majority of the companies that are still using Spark, you can expect to find some Scala codes that are much less optimized and much slower than what we used for the benchmark. You should also know that Spark has a huge number of obscure and undocumented parameters that might affect its speed. And normally, to get the best performances, you should spend your time to understand and tune all these parameters, so that all these parameters have a value that is optimal for your database size and your database structure. Of course, if your database size changes, you need to redo everything, to re-optimize everything, but that's another story. So we finally found a very interesting blog talking about these obscure parameters from Spark. The author of this blog, Michal Senkir, ran a large quantity of experiments with Spark. Michal experimented with many different Spark parameters. For example, here is a chart that summarizes what's happening when you play with one of the most important parameters. With the right value of this parameter, you can see a speedup of 1.2 compared to the default value of the parameter. I didn't do the experiment myself, but some friends with some years of experience in Spark are telling me that it's possible to reach a speedup of 1.5 and in some exceptional case even 2 when you play with all these parameters and find their optimal value. Obviously, each time that your data change, you need to recompute some other optimal settings, but you can, for a brief amount of time, get a small speedup. The thing is, even if you do spend several weeks tuning every parameter to perfection, you can expect to gain a speedup of maximum 2, and that will never allow you to match the speed of Anatella. To remind you, on some common TPCH queries, Anatella is more than 100 times faster than Spark. Up to now, we compared the speed of Anatella with Hadoop and Spark, and we found a result that is almost unbelievable. Anatella is more than 100 times faster than Spark. Spark himself is recognized to be 100 times faster than all the other tools in the Hadoop ecosystem. And I must admit that sometimes the reaction from some people when I am presenting these results is incredulity and distrust. And this is quite normal. Amazon, IBM and all these vendors have literally invested millions of euros and dollars for the promotion of Spark. And their message is always the same. Add more machine to get a shorter computing time. But this message is only true if the incompressible time is small. And for Spark and the vast majority of the distributed computation system available in the cloud, this message is false. Basically, the Amdahl's law is telling us a story that is in complete opposition against the marketing messages from Amazon. An honest marketing message should have been add hundreds of machines to reduce your computing time by 0.0001%. Actually, the reality is that the only ones that benefit from Spark and make huge money out of it are the cloud providers, Amazon and Azure. It's a little bit like a world where the old companies would give away free cars. You could guess that these free cars might not be very efficient in terms of gas consumption. And for those of you that still think that it's just totally impossible that Anatella has this super high, unbelievable speed, we found another interesting benchmark realized by Adam Drake. And Adam Drake is telling us that using some simple batch shell command line utilities that are available in all Linux systems since the 90s, it can run more than 200 times faster than a Spark cluster with only one laptop. That's even more than what I am claiming in the context of the TPCH benchmark. This might be surprising and unbelievable for you, but as I told you earlier, nearly any kind of properly designed C code can beat Hadoop and Spark. So let's have a quick look at the Adam Drake benchmark. Adam has a large database of chess games that is composed of 3.4 gigabytes of text file. And here is an extract out of one of these text files. As you can see, for each chess game, we have the name of the players, the date, the location, and the result of the game. Here, the result is 1-0. This means that the white player won the game. What we want to do for the benchmark is to count how many times the white player has won, how many times the black player has won, and how many times there was a draw game. Inside Anatella, this can be computed very easily using this simple data transformation graph here at the bottom. Inside this article, Adam Drake writes, for the same amount of data, 3.4 gigabytes, I was able to use my laptop to get the results in about 12 seconds, while the Hadoop processing took about 26 minutes. To get this running time, Adam Drake used some standard Linux shelled command line utilities. So the single laptop from Adam Drake is 235 times faster than the Amazon AWS Hadoop cluster. At the same time, Anatella is still slightly faster, 13% faster than the shell command line utilities from Adam Drake. And obviously 268 times faster than Hadoop. So if you want to reproduce yourself these results, the GitHub website is just there. So as you can see, Anatella speed might be high, but there is nothing really incredible or abnormal about it. Even an old tool from the 90s can achieve nearly the same speed. That's just another way to tell you that the results from the TPCH benchmark might be unexpected, but they are not abnormal or impossible to believe. There's just that Anatella is properly coded in C and Spark is not. Let's now go back to the Amdahl's law again. So we already saw this chart previously, but I'd like to show you something different this time. Let's look at this red point here. It represents a situation where your incompressible time is around 5%. It's a green line. And when you already are using 32 CPUs to do all your computation. Looking at this green curve, you can still see that it's interesting to buy more CPU. For example, if you add 32 CPUs, you go from 30 to 64, you get a significant increase in speed up. You go from a speed up of around 13 to a speed up of 16. You have a gain in speed up of about 3. Let's now say one more time that you have again 32 CPUs, but this time your incompressible time is around 25%, meaning that we are in this exact point here. In such situation, you can see that it's not very interesting to buy more CPUs, because the speed gain that you will get is almost zero. But even in this difficult situation, there is another way to gain speed. We could replace the 32 CPUs that we are currently using with 32 CPUs that are running faster, with a higher clock frequency. These high-frequency CPUs are more expensive than the normal ones, but when you are in this situation, with an incompressible time of 25%, that's the only way to reduce computation time and gain speed. Actually, we'll talk about the CPU prices later and we'll see some amusing things. I don't want to spoil anything yet, so just keep listening. So you can see here that depending on your incompressible time, 5% or 25%, it's sometimes interesting to add more CPUs, like here, and sometimes it's useless, like here. There are some workloads that are easy by nature. They will have a small incompressible time and then it makes sense for these workloads to use mini CPUs. But for the difficult workloads that have a large incompressible time, it's useless to use many CPUs. In this case, you want to use a smaller amount of CPU but faster, more expensive CPUs. In other words, the optimal number of CPU to run a workload depends on the incompressible time of the workload that you want to execute. For example, in this difficult situation, with a high incompressible time, it's better to have a small number of CPU but with a very high clock frequency, so that each CPU runs very fast. Your workload can be easy or difficult to parallelize. We have seen that in the case of Spark, the workload required to run the TPCH benchmark is kind of difficult workload, because it has an incompressible time that is above 50%, so it's a blue line. This is a blue line there. This means that Spark is not able to properly parallelize the workload and Spark stays very slow. So you should really avoid using Spark to do any workload that involves ETL tasks such as training table, aggregating table, filtering table. This is all very difficult for Spark. And the creators from Spark are not stupid. They also know that very well. This is why they are progressively changing their communication to promote Spark to handle a completely different workload, IoT real-time messaging. You see, when you do load balancing to send all the IoT messages between many different Spark servers, this is working properly with a small incompressible time, because it's not really distributed computation that you are doing, but rather load balancing between different web servers. So by using the Amdahl's law, we understood why Spark is so slow, but not everybody is interested in big data tools and high performance data transformation. What about applying our new knowledge about the Amdahl's law to another, more ground-to-earth situation, such as when you have to choose a new CPU for your next computer? More precisely, we are interested in the number of cores inside the CPU and the clock frequency of the CPU. A CPU with a large number of cores is good for this type of workload, with a small incompressible time, while a CPU with a very high clock frequency is good for this type of workload with a large incompressible time. So to try to find the best CPU for your next server, I found an amusing video by a Canadian YouTuber named Linus Tech Tips. If you are not interested by some advice on how to select a good CPU for your next machine, you can click here to skip this part. So some of you might argue that a YouTube reference has not its place in a serious video like this one. But hey, I don't know if you realize, but you are looking at a YouTube video just now. So since we are on YouTube anyway, why not use a YouTuber as a source of information? Plus, I like the guy, he is cool. So Linus did run some benchmark on the most common tools used to do all type of common tasks: 3D modeling, rendering, CAD, video editing, etc. And Linus did run this benchmark on two very different families of CPUs. Here on the left side, we have common grade CPUs with a relatively small number of cores, from 6 core to 8 cores. And on the other side, on the right side, we have high-end, very expensive CPUs reserved for high-end industrial application, with a high number of cores that goes up to 18 cores for this Core i9-9980XE. By the way, it's easy to know if a CPU belongs to the family on the right or on the left. You just look at the last character in the name. On the family on the left, the last character is a K. And on the family on the right, the last character is a X. So, the marketing people from Intel want you to believe that the expensive CPU with a X in the name on the right here are better because they have more cores. But both Linus and our newly acquired knowledge about the Amdahl's law are telling us another story. It's actually the whole point of the YouTube video from Linus Tech Tips. He wants you to know that you shouldn't buy these high core count CPUs. More precisely, the Amdahl's law is telling us that for some very specific workloads that are easy to parallelize, we'll have a small incompressible time, and for these easy workloads, it's interesting to have plenty of cores. So for these easy workloads, the X CPU on the right are the best CPU that you can use. But what about the difficult workloads? They do not parallelize very well. For all these difficult workloads, it's better to use this CPU here on the left, because they might not have a large core count, but each core runs very fast at a very high frequency, so your workload will still run faster. You can even see here that this Core i9-9900K can run at 5 GHz for a brief moment of time. So the next question is, how difficult to parallelize are the most common tasks that you regularly run on your PC? I made a small list here of some difficult workloads. These include using Office, playing video games, and running most machine learning algorithms. Okay, this last one is not so common, but for me it is. As you can see, these are actually the most common workloads that we do every day. So the X family on the right is definitively not useful for your everyday usage. But let's now have a closer look at what happens with the type of easy workloads that parallelize easily, such as 3D rendering. For this type of workloads, the X series of CPU should do better. Linus decided to use the SpecView Perf 13 benchmark to run some 3D rendering. This benchmark includes the most common 3D rendering applications: 3D Studio, CATIA, Maya, SolidWorks, and many others. And these are the results of the benchmark related to 3D rendering. You can see here that all the CPUs have about the same performances. All the bars in this chart have about the same length. And this is somewhat unexpected, because in theory, the X series of CPU that has many cores should normally give significantly better results. And it's actually not the case at all. In this benchmark, the best CPU are actually the CPU with the lowest core count. It's the Intel Core i7-8700K with 6 core here, and here it's a Core i7-9900K with 8 core. Here you can see some other benchmark results related to the rendering of a video in Adobe Premiere. Normally, this is again the type of easy to parallelize task, so that in theory, the X series of CPU with a large core count should be the best. But we can see that the best CPU, here the Core i9-9900K, has only 8 cores. And here, despite having only 6 cores, the Core i7-8000K is practically as fast as this very expensive 18-core CPU. So just by running 0.7 GHz faster than the 18-core CPU, this old Core i7 is able to match the performance of the 18-core CPU. So at the end, what does this mean? It means that the incompressible time for all these easy workloads, it's not as small as you would expect. And a large incompressible time always greatly favors the CPU with a small number of cores and, more importantly, a high frequency clock. This is again an example where the Amdahl's law makes distributed or parallel computation nearly useless, or at least not very useful. Actually, you should know that it's kind of difficult to design a distributed or parallel software solution that is really scalable, that has a small incompressible time that correctly speeds up when you use more cores. In terms of compressible time, the examples that are given here by Linus Tech Tips are very representative of what you can expect in almost all software tools. We didn't cherry pick this example. Linus Tech Tips just included this example in its benchmark because they are the best and most well-known software in each of their category. So what can we conclude from all the benchmarking from Linus? The conclusion is that you don't need a large number of cores in your CPU, and in the same way, you don't need a large number of nodes in your cluster. What you really need is a small number of very expensive CPUs that are running very fast with a high clock speed. This will produce the best times with almost all tools, including Timmy and Spark. Actually, if you are lucky enough to have an easy workload that can easily be parallelized, and you are really lucky because these type of workloads are very uncommon, you should rather use a software that does all the computation on your GPU, like this one, your graphical processing unit, and not your CPU. You might also wonder why Intel and AMD are always releasing new CPU with a greater amount of cores and not with a higher clock frequency. That's because it's now becoming almost impossible to increase the clock frequency of the CPUs. Everyone is stuck at around 5 GHz. So the core count is the only commercial argument on which Intel and AMD can still fight. But it's only a commercial argument. In reality, a CPU with a high core count won't make your computer run faster. And actually, it's even the opposite. Because when you have a CPU with a high core count, you also have a CPU with a small clock frequency. So that at the end, your computer is slower when you use a CPU with many cores. So now you know which CPU you need to buy for your next server. Just select a CPU with the highest performances on one thread. It's usually the CPU with the highest clock speed. And you don't need to really care about the number of cores, 6 or 8 cores, it's very common and it's also very good. A higher number of cores is most of the time useless. At the end, these examples are just here to tell you how difficult it is to design a software that correctly speeds up when you give him more cores or more CPUs or more nodes. Even the best engineers working on the most well-known application for 3D rendering and video editing could not achieve a software that correctly speeds up. So it should come without any surprise to you that Spark is not able to correctly speed up neither. So the next logical question is, what about Timmy? Is it able to correctly speed up? What's the incompressible time of Timmy? So during the course of this presentation, you might have noticed that I am not a big fan of distributed computation system. It's just that I have seen so many companies investing millions in huge hardware infrastructure, while at the same time, one PC equipped with practically any C program would have run faster. For me, it's just nothing short from terrible. So let's now see how we might be able to design an efficient distributed computation system. And if you are not interested on how we design the distributed computation system used inside Timmy, you can click here to skip this part. And the most important keyword here is efficient. It's easy to design a distributed computation system, but because of the Amdahl's law, it's actually very difficult to make it efficient. Indeed, one of the worst examples that you can find is Spark, with almost all its queries at an unexpected 50 incompressible time that are illustrated here in red. You should know that the Amdahl's law is applicable to all distributed computation systems. It applies to Spark, obviously, but also to Hive, Redshift, MongoDB, Oracle Exadata, etc. The Amdahl's law is not a particular problem just for Spark. It's a big problem for all distributed or parallel computation engines. Now the question that you should ask yourself is, how many software editors know about the crucial importance of the incompressible time before seeing this presentation? Did you care about the incompressible time before seeing this presentation? But no, of course not. And the same is true for all these software companies. And the direct consequence is that 99% of the distributed computation systems that are actually available on the market are completely rubbish. The only thing that they do is heating the globe without producing any noticeable increase in processing speed. If you're searching for a reason why the temperature rises all around the Earth, why the ice caps are melting, don't search any further. You just found a big one. Ignorant software companies that knows nothing about the Amdahl's law. And one of these companies is obviously Amazon, since they literally invested hundreds of millions of euros to promote a deficient technology. Although, in the case of Amazon, it's not because they are stupid that they are promoting all these deficient technologies like Spark, MongoDB, Redshift. It's just because they can sell more servers like that. They are just greedy. There are basically two strategies to do distributed computation. The first strategy, here on the left, is the one used by Spark. In this first strategy, each time we run one of the TPCH query, we use all the computers, all the nodes inside the cluster. This is why the name of this strategy is one query per cluster. That's because when you run a query, the whole cluster starts running. So to run the 22 queries from the TPCH, we first run the query 1 using all the cluster, all the nodes in the cluster. And then when it's finished, we run the query 2, again using all the nodes in the cluster. And after query 3 and so on and so on. And we have seen in the previous slide that this way of proceeding, it's not very good, because when you distribute your computation like that, you have an incompressible time that is between 20 to 50%, so that it does not scale up properly. Then you have this second strategy that is illustrated here on the right. Instead of trying to distribute the computation of one query, like here, we will distribute the computation of a bundle of query. In this case, the TPCH benchmark, the bundle is composed of 22 queries. So in this second strategy, we only use one computer to run a query. This is why it's named one query per node. So to run the 22 queries from the TPCH, the first node here will run sequentially the queries 1, 2, 3 and 4. And at the same time, you will have the query 5, 6 and 7 running on the second node. And at the same time, the query 8, 9 and 10 will run on the third node, etc. You can see that proceeding like that, we are using all the nodes in the cluster simultaneously. This way of distributing the TPCH workloads is very good because it has an initialization time or incompressible time S that is almost zero. More precisely, Anatella just needs to send the SQL query to execute to each node, and this is almost instantaneous because the file that stores the SQL query is just usually around 1 or 2 kilobytes, and sending 1 or 2 kilobytes over the computer network is almost instantaneous. Since the initialization time or incompressible time is zero, this means that Anatella is truly infinitively scalable, and we can really achieve speed up above 1000, while at the same time Spark is still limited to a speed up of maximum 5, just to remind you. As a side note, you can also set up Anatella so that it runs one query per cluster, in the same way as Spark is doing. But this is usually not very efficient. It's still more efficient than Spark, but we are still hurt by the incompressible time that is non-null in this case. You should realize that the strategy on the right here, the one query per node strategy, is the one where we have the best efficiency. 100% of the running time is used to effectively do the computation required to get the answers to these 22 queries from the TPCH. In other words, when you use the solution on the right here, you will not lose any time to manage how the workload is distributed on several nodes, because there is almost nothing to do to distribute the workload. You just need to send the 22 SQL commands to the 7 nodes, which is almost instantaneous. On the contrary, here on the left, more than half of the running time is spent doing zero useful computation. More precisely, more than half of the running time is used to simply run the data pipeline that is used to distribute the workload between nodes, and this is terribly inefficient. So the next question is, why is Spark not using the one query per node strategy? Because it's a much better strategy. And the answer is, it could use this strategy, but it would be very unstable. You see, Spark is an in-memory tool. So what does it mean, in-memory tool? This means that when Spark executes a SQL command or a data transformation, it first loads into the RAM memory of the computers all the data required to run the data transformation. And if the data is very large, you really need to use all the RAM memory from all the machines from the cluster to execute your SQL command. And this is exactly what's happening here on the left. The query 1 is executed using all the RAM memory from all the computers in the cluster. In opposition, here on the right, the query 1 is executed using only the memory from the first node. So if this query 1 manipulates a large quantity of data, you won't have enough RAM memory to feed all the data, and Spark will just fail and crash. And I think that it's exactly what happened on query 15, by the way. So we were not able to run this query 15 in a reliable way. It did work a few times, but it's definitively not stable at all. So to summarize, yes, you could set up Spark to use this most efficient strategy, one query per node. But if you do that, you'll get a very unreliable system. And in any way, I would definitively advise you to avoid doing that in any production environment where you need stability. So the next question is, what about Anatella? Is this one query per node strategy a really viable and secure strategy to use with Anatella? Or will it crash all the time, like when we are using Spark? In other words, can Anatella process a very large database using only the limited amount of RAM memory available in one PC? How stable is Anatella when it needs to run queries on a petabyte or even an exabyte database on one small PC? So to try to answer this question, we measure the RAM memory consumption of each of the TPCH query on the 1 terabyte database. The results are visible here in this table. And you can see that on average, the RAM consumption is less than 3 gigabytes. This means that when you are using Anatella, you can manipulate terabyte-sized databases using less than 3 gigabytes of RAM memory. This is really a technical prowess to be able to do that, and we are kind of proud of these results. Some of you might have noticed that some queries are using much more RAM than the others. For example, the query 3 here uses more than 10 gigs of RAM. And this is actually a design choice. When we wrote the query in Anatella, we decided to use more memory to get the best and shortest running time for the benchmark. But if you are not in a hurry, you can also run the same query slightly differently, and then the RAM memory consumption dropped to only 2 gigabytes. That's practically nothing. As a comparison, you should know that Spark is also using around 3 gigabytes of RAM, but to execute queries on a database that is 1,000 times smaller. Not 1 terabyte, but a 1 gigabyte database. Just fun. But this memory consumption was to be expected, because Spark is, after all, an in-memory tool, and all in-memory tools need a large quantity of RAM memory to run. Let's now talk about money. Because it's very good to have a very fast data transformation engine, but it's even better when this data transformation engine does not cost you a leg. So if you are not interested by this part, you can click here to directly go to the summary. So in the cloud, prices are roughly proportional to the duration of your computation. The longer the computation, the more you pay. So we again start from the TPCH benchmark, and we compute the total time required to run the whole benchmark, the 22 queries, when we only use one CPU. It's here. We decided to use one CPU to run the computation because this means that we are following the one query per node strategy, which is, as we have seen earlier, the most efficient strategy available. I should definitively advise you to avoid doing that in any production environment because you'll get a very unreliable Spark system. Spark is very unreliable because of the very limited quantity of RAM available to run the computation. But let's now be optimistic and assume that we don't have any crash at all. In this condition, the total running time of Spark will be around 22,000 seconds, while the total running time of Anatella will be less than 1,000 seconds. So in other words, Anatella is more than 22 times faster than Spark. What does it mean in practice? Let's assume that you pay each year around 22,000 euros to Amazon to run your computation in the cloud. Since Anatella is 22 times faster than an unreliable Spark infrastructure, you'll be able to divide this 22,000 euros by 22. And at the end, you only get at the end of the year a bill from Amazon for an amount of 1,000 euros. Now, you still like to have a reliable Spark system, and you decide to buy on Amazon a small cluster of just 10 machines instead of one. Now you can run all your queries on 10 machines. But obviously the infrastructure cost will be multiplied by 10. But at the same time, since you are now using many machines, the running time is reduced. You get a speed up. And the Amdahl's law is telling us that you can expect a speed up of maximum 2 on an infinite infrastructure size. But let's just say that again we are lucky and that we already achieved this speed up of 2 using our small infrastructure based on only 10 machines. So at the end, to get a reliable infrastructure to run your computation, you need to multiply by 5 the price of your reliable infrastructure. Indeed, the infrastructure cost is multiplied by 10, but the running time is divided by 2 because of the speed up, so that at the end we have a factor of 5, 10 divided by 2, between the cost of the unreliable infrastructure and the cost of the reliable infrastructure. So to summarize, at the end, we see a factor of more than 100 between Anatella and a reliable Spark-based solution in the cloud. And if you decided to go full Hadoop and you bought 50 machines to run Spark, then the situation is even worse. You'll pay more than €500,000 to get something slower than an Anatella infrastructure that only costs €1,000. Now you understand why Amazon is investing millions of euros in marketing around Spark, Redshift and all these flawed distributed computation systems. When you use Spark, you don't have any choice. You need this very large infrastructure with dozens of servers. On the other hand, when you are using Anatella, you don't need many servers. Usually one big server is more than enough to process all your data, even if you are a telecom with a very large volumetry. And hosting one server is very easy. You don't need Amazon for that. You can easily host yourself your own Anatella server so that in this condition you have the freedom to choose to avoid the cloud. You see, there exist many cool solutions in the cloud. Gmail, Google Drive, OCRM, Salesforce, etc. But personally, I advise you to avoid the cloud for everything related to data science. It's slow and it's much more expensive. And it's really risky for non-American companies. You'll find more information related to this last topic in the video from Mr. Frédéric Pierucci. Just click here to see the video. I invite you to watch the presentation of Mr. Pierucci. It's unfortunately in French, but it's very instructive. Here is a quick summary of the presentation. So if there is one thing that you should remember out of this presentation is this. Spark has this huge incompressible time that limits the speed up that you can get with Spark to 2 most of the time. As a consequence, since it's not able to properly speed up when you add more nodes, it's easy to run faster than Spark. And that's exactly what Anatella can easily do. One Anatella server is several orders of magnitude faster than a whole Spark cluster. Furthermore, if you really want to do distributed computation, the default strategy used by Anatella to distribute the workload, that is named one query per node strategy, allows to reach very high speed up, value above 1000 are possible. Again, to remind you, Spark is limited to speed up of 2. Next is reliability. During the TPCH benchmark, Spark failed a large number of times when it tried to execute query 15. You see, Spark is an in-memory tool. It must have a very large quantity of RAM memory to process in a reliable way your queries. And if you have some queries that involves manipulating very large table, it will fail out of memory. In opposition, Anatella is not an in-memory tool. It can process practically any database size. Next is the price. If you replace Spark with Anatella in the cloud, your Amazon bills will be divided by a factor of 100 approximately. And the next point is again the cloud. With Anatella, you have the freedom to decide to completely avoid any cloud infrastructure. While in opposition with Spark, it's really difficult and expensive to avoid the cloud. And when you can get rid of the cloud, you get much higher computation speed, much lower cost, and if you are a non-American company, a much more secure infrastructure. Also, since Anatella is a much faster ETL tool, the processing time is reduced by a huge factor. And this is very important because typically ETL tasks consume more than 80% of the time of your data scientist. This means that the efficiency of your data scientist is usually multiplied by a factor of 4 to 11. This increased efficiency means that your data scientist will produce much more results and therefore generate much more value. It's hard to estimate the value of a good discovery in your data, but personally I think it's too silly to miss out on the golden egg because I don't have a tool that is fast enough to properly investigate my data. Furthermore, Anatella will allow you to avoid getting really bad headaches each time that you must fix a bug or improve your ETL processes. No headaches. You see, to use Spark, you need to write Scala code, and the whole industry agrees on one point. Scala is a terrible language, difficult to write and even more difficult to maintain. In opposition, in Anatella, all data transformations are represented through a user-friendly graphical interface that is really easy to understand and maintain. And finally, you should know that Anatella has a community edition that already covers 99% of the typical use case that you find in companies. So you can download Anatella now and see by yourself how cool Anatella is. You don't even need administrative rights to install and run Anatella, so there is absolutely no excuses to avoid trying it. Back in 2007, we only had one tool, our automated machine learning solution, Timmy Modeler. Timmy Modeler gets world-level machine learning competition results in a fraction of the time. But unfortunately, back in 2007, nobody wanted it, because it's actually pointless to be able to create a very good model in a few hours when it takes several months to process the data beforehand. We had a perfect solution to a problem that did not exist. This is why we created Anatella. You see, with Anatella you can now reduce your ETL processes to a few hours maximum. And then it makes perfect sense to use a fast, automated machine learning solution such as Timmy Modeler. In this way, using both Anatella and Timmy Modeler, we now offer one of the best data science solutions. We offer the best solution for ETL procedures that still consume at least 80% of your time, and for the remaining 20%, we offer you one of the best automated machine learning solutions, Timmy Modeler. Also, to guarantee even more efficiency, Timmy integrates flawlessly with all the major data visualization solutions, such as Skibella, our own free BI solution, Tableau or Qlik. Basically, you won't find a better data science solution anywhere else. Timmy is just the fastest, the most efficient and the most versatile data science platform currently available. So this presentation is now finished. I hope you enjoyed it. If you need more information about Anatella or Timmy, I invite you to visit our website, timmy.eu. Also, don't hesitate to download Anatella. Anatella is directly available on the website, timmy.eu. It's a direct and open download. It's only 80 MB to download, so no excuses. Have a great day. See you!